Secondary Calc, the optional homework. No. Did that work? Oh, this is the optional homework. Yeah. We're live now. Quickly. Hello, hello. I was not under the impression that most people were planning to do the optional homework questions, as nobody had, I don't think anybody had really posted them or told me about them until today. So I've only looked at the questions for a couple of minutes apiece. Is it all due at midnight? Is that right? So let's just get right into it. It looks like the first problem, and again, I haven't worked any of these out myself. I've just looked at them for literally maybe a minute apiece. But it's this pretty obnoxious looking function. What is this? Negative 2 less s less than 0 minus sine of s cubed if it's between. And the idea here is that you're talking about some g of x function is going to be the integral, right? So g of s ds. And the idea behind this problem is you can't seem to input the functions into Desmos or Symbolab. Oh, I see. You're trying. Look, we're gonna try to use the fundamental theorem of calculus here, right? So the idea here is that the fundamental theorem of calculus more or less says that when you take ddx, it's almost like the derivative and the integral just sort of cancel. It's very hand-wavy, but the integral is called the antiderivative. Yeah, there's an idea that the notions are, the integral is sort of the reverse of the derivative, and vice versa. So the idea here is they're asking you about the critical points of g, which means that you want to look at the derivative of g, which is more or less g of s, little g of s. So I think that should be the motivation you need to leave the value of the function g as these points as a mathematical expression. Do not try to find a numerical value. Yeah, that's basically all I can tell you about that without having thoroughly solved it myself. Again, I only had a couple of minutes to look at each of these. But yeah, I hope that should be fine, right? Once you know to look at the derivative in order to get the critical points, then you can just look at small g, the function small g, and that should be able to get you what you need. So next problem, Q2. See what I'm saying? Look at small g. So there was the first derivative test, I believe, is saying something like, what? Some point over here is a max. If for some delta, so maybe this is the function, x and f of x. And what this is saying is basically there's a little bit of a, so if this is point C, we'll call it, there's like a C minus delta and a C plus delta. This is the original definition, right? Such that I think what it's saying is that the slope is positive up here, right? It's uphill, and the slope is negative down here. It's downhill, right? The fundamental theorem of integral calculus was about getting the antiderivative. Yes, but it's also going to, just look at Wikipedia, right? If you just go to Wikipedia, fundamental theorem of calculus, it sort of has a couple of forms, and one of them is essentially telling you that the derivative and the integral cancel out just like you would hope. Yeah. Anyways, that's the hope. Again, I haven't looked at it very carefully. I haven't thought about Riemann integrability in years. But it was not clear to me how you would do the question without just looking at the derivative. Yeah, here, let me post the fundamental theorem of calculus in the group chat. Okay. So anyways, question 2. The original theorem is saying something like, if you know that everything within some, everything to the left has a positive slope going uphill, and everything to the right is going downhill, you can kind of conclude that the point that you have in question is a maximum, right? Okay, you could of course switch the uphill and downhill. Doesn't really, well, actually no, you couldn't, because then it would be a minimum, right? But the point being, instead of calling it a little delta interval, now they're trying to tell you a very similar story. They're saying that there's only one critical point, right? And they're trying to tell you that some point over here has positive slope. What is going on with my pen? Some point over... Interesting. My screen appears to have a dead zone. What the heck? A positive sign. And over here, a negative sign. What is this like? I think this is like A star, point A star. And this is B star. Right? So, like, intuitively, the fact that this is positive right here, the slope is positive right here, and there's only one critical point, you can kind of see why the slope everywhere here has got to be positive, right? And the slope everywhere there has got to be negative. Which is kind of your hint to choose delta to be... It's basically your hint to choose delta to be within these bounds, right? Because if you... A star and B star might not be the same distance from within, but the idea is just shrink your delta small enough so that it'll fit within both of them, and see if you can play around with that idea and make, for that appropriate choice of delta, see if you can make one definition turn into the other. Should we use the intermediate value theorem? I don't think that will be helpful. What intermediate value theorem is basically saying that if some function has, a point here and a point here, it's got to hit every point in between, right? And it's continuous, of course. It's got to hit some point in between. I don't see how that would help you, right? But for this problem, the intuition is that because you know that some point has a positive slope, right, over here, and some point has a negative slope over there, and you only know that there's one critical point, the fact that it's positive over here means it's got to be positive nearby, right? So, I don't know, try to see if you can throw a theorem at it to make this rigorous. I mean, I haven't thought carefully about the intermediate value theorem, but intuitively I don't think it's relevant. But you need to think about how to prove that, you basically got to turn this situation into this one over here, right? Given this situation, you have to show that, in fact, it's this situation. Show that, show you can reduce to the existing theorem. Yeah. Onwards and onwards. Okay. Question 3. To show... Yeah, so question 3, I don't know, is it hard? I didn't look at it thoroughly, but I think it should be relatively similar to the problem you have already worked, right? Use your definition of differentiability, continuity, to show that it's differentiable and continuous at the points in question, and then show that it's not differentiable at 0 is the last part. I haven't worked through it myself. I don't know if there's any, like, curveballs in there. Yeah, okay. Let's see, what's 4? Yeah. Do people want to look at question 4? I think I saw it pretty quickly. e be the function. Right, so question 4, right? It's sort of saying if your function is basically, what is it, like x sine of 1 over x, it's going to look like, being bouncing between these values. The left-hand side is going to look something similar. I'm not going to worry about it too much right now. But the idea here is want to show, or we want to, WTS means we want to show there exists, what is it? Given an arbitrary epsilon, use theorem to prove there exists some c such that 0 is less than c is less than epsilon, and e prime of c is equal to 1. And the statement of intermediate value theorem, I'm not going to write it all out because it's just too much tediousness. But the thing you got to get careful is what are your open intervals and what are your closed intervals. So it's saying, or sorry, this is mean value theorem. It's differentiable on a to b open and continuous on a to b closed. And it's saying that this is equal to f of b minus f of a over b minus a. So I guess we're using capital E as a function instead of f. But the idea here is, look, this corresponds pretty closely. We want to shoot for fb minus fa over b minus a. We want this to be equal to 1. Right? This is what we're shooting for. I think it's pretty clear that the left endpoint a is equal to 0. We need to choose a is equal to 0 because we, I don't know. I don't know how to exactly explain that it should be clear, but I feel like it is, right? Yeah, except for are there even epsilons? Yeah, there are epsilons in this problem, but I don't think there are deltas. Well, the point here, how do I explain it? The point here is that, okay, if the left endpoint is a, and you choose like epsilon to be the right, epsilon is not the right endpoint, we want to choose the right endpoint to be between a and epsilon, right? We want to choose the right endpoint to be between a and epsilon. So we know that a is equal to fa is equal to 0, right? So over here, this fa is 0 and that a is 0. And again, I feel like it should be reasonably obvious that the left endpoint should be 0 because that's kind of like one of our points of interest, right? It's kind of our point of interest. Or like, how do you put it? We're trying to choose an epsilon between, positive, so let the left endpoint be 0. So basically the idea here is we're trying to find an FB and B that are equal to each other. So we basically want to find f of b equal to b, right? We want to find a b such that b is equal to fb and I guess also b is less than epsilon. So basically we want to prove that you can always find some b that serves as your right endpoint in here that's less than epsilon such that b is equal to f of b. And what is f of b? This is saying b is equal to b sine of 1 over b. So this basically happens whenever sine, this basically happens whenever sine of 1 over b is 1, right? So like intuitively, this is a point where b is equal to f of b, this is a point where b is equal to f of b, and so on, and so forth, and so on, and so forth, right? Every single time that happens, b is equal to f of b at one of the peaks. You see what I'm getting at here? It's saying that basically no matter what value of epsilon you choose, let's say epsilon is right here, show that you can always find one of these special values, right? Show that you can always find a b. Yeah, it should be a mathematical expression. You're not going to be able to find a straight up number. It's you should prove that some b can always be found less than epsilon, right? The worry is that epsilon is so small that you can't find a b. You have to show that no matter how small epsilon is, you can always find one of these. So it's very similar to the first homework assignment problem with the Limites, I think. So think about how you would do that. Okay, I think that's probably all I can say about that one without giving too much away. But yeah, once you can guarantee the existence of a b, then the rest of the problem is basically just invoking mean value theorem. The meat of the problem is showing that such a b can always be found, right? And you've done this before in homework 1. Okay, all right. So yeah, once a b is found, just plug it into mean value theorem, right? And because you chose b such that f of b over b is equal to 1, you're done. Yeah. So the very end is simple. It's just that the meat of the problem is showing you can always choose a b no matter how small epsilon is to satisfy the property f of b is equal to b. Okay, good so far? Let's see. What do we have next? Yeah, it's, I don't know why everyone was asking so much about this one. It seems, so question 5 seems pretty much identical to the example you were given on the previous set, right? Where now, before we were talking about locally constant, now we talk about locally increasing. And there we had to show that it implies constant over the entire interval. Now we have to show that it implies increasing over the entire interval. AB over... So, I don't know. How do you want to do this? Maybe let's just remind ourselves of the arguments of locally constant first and show how the locally increasing is really similar. So the idea is that, let me draw a graph here. Let's say that this is A, this is B, right? And they're inclusive. And locally constant is basically saying that, so if this is X and this is f of X, it's basically saying that there's a little delta interval next to A that's constant, right? And there's a perhaps different delta interval next to B that's constant. And, for any point in between, for any point, I guess, X in between, there's a little two-sided delta, and this delta could be different for every X. And the idea is that you have to show that, I'm drawing these as different heights to emphasize what we're afraid of, but in fact, we're trying to show that each one of these heights is actually the exact same thing to show that the entire function is constant, right? So that's the goal. And the way that we did this was we basically considered W as the supremum of that set S, consists of all the right endpoints, little s, such that 0 to s was constant. So again, you can take a thorough look at capital S if you want to, but the basic idea is it consists of all the right endpoints little s such that the function is constant over the interval 0 to s. And the idea here is that, okay, now you can rule out, you're trying to show that, you want to show that W is equal to B, and to do that, you have to rule out W is equal to A, or W is in between. It's pretty easy to rule out that W is equal to A. I'll let you remind yourself by looking at the proof. But the kind of hard case, the meat of the problem, or the meat of the idea, is when A is less than W is less than B. And to do this, we know that because it's, in the middle, there's going to be some delta interval on both sides. I'm going to draw it really big just to exaggerate it, right? But the idea is now we need to show that W, we need to find a contradiction, that W is not the supremum. And we start by assuming that it is the supremum. So that at W minus delta and W plus delta, we get a function that's locally constant, right? And perhaps it's different heights than everything else. But we need to show that. What do we want to do? Well, the argument is kind of technical, right? We start by noting that W minus delta, because W is the supremum, W, which is the least upper bound, W minus delta is not an upper bound. Which means that some point S, let's call it little s, can be found in between here, right? Some point little s that's inside the set big S. And because you have the set little s, because you have a little s that you can squeeze in between here, because it's in set big S, that means that there exists some constant function that's, there exists some function, or rather the function is constant on 0 to s, right? And the fear is that this thing right here might be a different height from this thing right here, but obviously that can't be true because they both include f of s, right? This point right here is f of s, and this point right here is f of s, so in fact these two things must be the exact same height, right? That's the argument. They've got to be the same height because they're both constant, and they agree on point S. So I'm going to redraw it. That means that this entire thing has got to be, all the same height. And once you get here, you're pretty much done. You just say, oh, well, let's look at some point over here. Let's call this, I don't know, Z or something. And you just notice to yourself that Z is, the function is constant from all the way over here to all the way over here. And that violates the, that obtains a contradiction that W was the least upper bound. The fact that the interval 0 to Z is constant means that W was not an upper bound at all. You see that? Basically, the fact that you can show that this function all goes constant past S means that S is not an upper bound, and you've got a contradiction. So locally increasing instead is, almost exactly the same, right? You've got a point A and you've got a point B, and it's basically saying, okay, it's increasing near A. You don't know exactly how it's increasing. It might be a little bit funny. But near B, it's also increasing, which is to say that B is greater than the stuff immediately to the left of it. And for any other point, it's going to look something like that. And I'm drawing these as not entirely straight lines, right? It could look something like this, for example. You don't know exactly for sure. But the idea is much the same, right? You basically just choose some point S, and you choose a delta on each, and by the definition, you have an S minus delta on each, and an S plus delta on each side. Excuse me, I should have called this W. W as the supremum, the least upper bound, W minus delta, and a W plus delta. And the idea, just like before, I'm going to draw this a little bit larger, right, is that you're going to choose some S in between W minus delta and W, and you're guaranteed that this is doable because W minus delta is not an upper bound. And the fact that you know that S is inside big S, which is now the set of all right endpoints, little s, such that 0 to s is increasing. So it's the exact same definition here, except for now it's just increasing, right? So the fact that little s is inside big S means that the function from 0 to s is increasing all the way up to s, right? And because you can just think about riding this line upwards, right? This line is going upwards, you can ride it up. And then once you get to s, now you're inside the neighborhood of W. So you can just continue to ride this line up, right? It's like sort of, I don't know, it's sort of like two separate roller coasters, right? You have sort of roller coaster 1 that takes you upwards. And once you get to S, you get off and you ride the other roller coaster further up, roller coaster 2. So in fact, you can think about everything as just one large roller coaster that just keeps bringing you up and up and up and up. Right, the goal of these questions is to show B is equal to W, and you do that by showing that B can't be equal to anything else. You show that B can't be equal to A, and you show that B can't be between, sorry, W can't, excuse me. You show B is equal to W by showing that W is not equal to anything else. You show that W is not equal to A, that's pretty easy, and you show that W can't be between A and B. That's the hard part, right? But the fact is, I think all you need is just the 1s, right? The fact that this function is increasing from 0 to s, and gets you half the way there, and then the fact that because it's close to W now, within the parentheses, you're guaranteed that the function keeps writing upwards too. So for any point in here, let's call it z. Well, now going from 0 to z is just one long upwards thing, right? I drew this kind of poorly. This should be entirely going upwards. Right? So this is just a non-stop upwards roller coaster from 0 all the way until you get to z. And you contradict the fact that W was an upper bound. Yeah, I mean, I feel like I haven't really done anything new. I've just basically read off what the example was, right, and changed the language to be talking about upwards instead of constant. That's all you need to do. Okay, good. Last one is showing that some point, right, trying to find the closest point or something like that. And the way you do this is just use the distance formula, right? It's the square root of x minus, so if this point is like x naught and y naught, right? The distance is x minus x naught plus y minus y naught, where y is equal to x squared. Right, so you can plug that in. And you're basically just going to take the derivative to minimize the distance. The only issue is this is nasty because of the square root, right? So the classic trick for these problems is to, instead of minimizing d is hard, you can minimize d squared instead, which is much easier because that gets rid of the square root. And the reason this works is because you note that d is a always positive function, right? How exactly do you explain this? Like, this is a function of one variable, right? Once you plug in y is equal to x squared, it's a function of one variable. It's always positive. So whenever d obtains a minimum, d squared should also obtain a minimum. You can, you have to go through a little bit of calculus to show that that's true, but I'll leave that bit to you, okay? Hopefully that shouldn't seem too strange. I don't think it, question 5, I don't think question 5 requires you to do 2 points like the linear case. Yeah. Anyways, that should be all you need, right? Well, I hope you all are having a nice final season. Yeah, I've been told by a lot of students in this class that they're planning to switch over to the applied calculus track for semester 2, and I think that's fine. Honestly, I don't think you necessarily need to do theory-based calculus the first time you see Calc. But yeah, I'll be around next semester. I don't have as much time because I'm a little bit busier, but I'll be on the Discord. And if there are questions that people want addressed, you can let me know, and we can schedule a session maybe one or two nights a week. Yeah, I don't know why people are focusing so much on the derivative or 2 points for the increasing problem. You're not even guaranteed that a derivative exists, right? You're not even guaranteed that a derivative exists. And I don't see why you would need a second point. Maybe I'm confused. Can you... Why would you need a second point? Because you're not trying to argue that the functions look linear or look constant anymore, right? You're trying to argue that it's increasing. And the fact that s is inside, little s is inside big S, guarantees that this entire segment is increasing. And the fact that w minus delta to w plus delta, the fact that w is in the interior means that this entire segment is also increasing. So when you put them together and use s as sort of a intermediary, sort of a transit point, you can kind of conclude that everything is increasing, right? Like, is there anything more than it? Yeah. Anyways, yeah, I think I gotta go log off because I've got some stuff to do. Yeah, I do think it's a little bit simpler than the linear case. But yeah, I would appreciate it if you could, hit the like button. I'm trying to take a different approach to this channel next semester and do some prepared content. But I would like to grow the channel and find more people to help in my free time as a hobby. So yeah, take care, and you'll see me around. Let me know what calculus problems or homework problems you want to tackle next time. Good evening, folks, and good luck. Oh, thank you. It's been nice learning. I think this is the first time I've seen your username, so I appreciate you dropping a comment at the end of semester. I think it's cool. I think it's been a cool experiment. But, yeah, I'll continue trying to help out in my free time. Just, I don't have as much free time anymore. Alright, folks, I think that's the end for today. Good evening.